Next up is Justin K here from AI.fish. There you go. Great. Excellent. So next up we have Justin K from AI.fish. He's going to be giving a presentation on innovative applications of artificial intelligence towards a sustainable and resilient blue economy. Justin, thanks very much. Welcome.
Okay, hi everybody. Thanks for having me. And thanks to the organizers for all the hard work making this happen. It's awesome. So my name's Justin Kay. I'm the CTO of AI.fish. We are an AI company specifically focused on applications in ocean conservation. We're really a full stack AI and software company. So we have an AI team with researchers from kind of all over, from MIT, CMU, NVIDIA. We have back-end and front-end software developers, and then we have people with fisheries expertise in-house that help us kind of figure out what it is that we should be working on. So Jimmy's here with me. We're the co-founders. Jimmy gave a talk earlier today about some of the products that we've built out for analyzing electronic monitoring footage and turning this into a product that helps review. I'm going to talk a little bit more about the R&D side of our business and some of the emerging opportunities that we're working on. So the main thing that we work on is computer vision. This is a subset of AI that's focused on image and video analytics. Specifically, we do a lot of projects in visual recognition. This is a subset of computer vision that deals with trying to figure out what exactly is in an image or a video and say something about what's happening. And so this includes things like object detection, so where is the object that you care about in the image, classification, what is the object, things like that. And so I'll talk about how that relates to electronic monitoring. We have quite a few different projects going on. We have a pretty big R&D team. And so I'm going to talk about two of these today, specifically the ones related to fisheries electronic monitoring. So we have a long ongoing project in long-line electronic monitoring, where the goal is to detect where the fish are, predominantly tuna or ground fish, say how many were caught during a period of time and what species they were. We've also got some recent really exciting work in trawl electronic monitoring, where we are looking at big piles or nets of fish and trying to say what is the apportionment between the different species or species groups. We've also worked with freshwater fish monitoring, so using sonar cameras, trying to track salmon populations during their seasonal migration. And then we've also done some additional work in ecology, where we're trying to count seal populations over time using static camera traps, which has been pretty exciting as well. So I'm going to focus on two of those today. And kind of the way that we get there. So how do we go from nothing to booting up a project? And the first thing that we do is we focus on building out a data set. We use machine learning algorithms, which are very data dependent. If you have good data, you can get a good model. If you don't have good data, you're kind of stuck with a bad model. And so we've built out an entire in-house annotation team and multi-step data annotation process, where we get very large amounts of bulk video. We process that into something that the machine learning algorithm can use. And then we have a combination of people who are dealing with the detections and the tracking annotations, as well as experts coming in to do the species ID. And so importantly, we're sourcing this from real-world fishing contexts. And so the data is more challenging if you do this versus sourcing it from perfect conditions. But this is the way that you can then get the algorithms to work better later on with challenging data in the field. And so this is an example from our Longline project, from two projects that we did, funded by NIFWF, where we collected nearly 2 million annotations on vessels in Alaska and Hawaii. This is the largest annotated detection and tracking data set that we know of in electronic monitoring. And so this lets us train highly accurate models that far surpass off-the-shelf options. And this is growing. So this was a project this completed last year. And so I think we're coming in on 3 million now, which is pretty exciting. And so doing this, we combine this with custom algorithm development. And so we can feed in really high quality data to get the initial models, and then we can develop custom solutions that really allow us to specialize them to different applications. And so specifically for tuna and swordfish longline, we're comparing here on the left, this is our algorithm. On the right, this is an open source solution. It's from Viame, which is a great piece of software. I'm not trying to rag on Viame here, just comparing it because it's an open source solution. This is a really challenging example where you have a fish coming on board and there's multiple fishermen kind of processing it, and it's getting hidden and kind of coming back into view over and over again. This is really challenging for computer vision algorithms. Every time you get a new frame, it's very difficult to say whether or not this is a brand new fish. If it was hidden for a while and then it comes back into view, for example. And so we've worked very hard to address this exact problem with some R&D funding from NOAA, as well as some grants from NIFWF. And so in this example, we correctly say that this is one fish, whereas the open source option out there says it's 14, which is not very good for accounting. And so we took these algorithms and moved into the Alaska Fixed Gear program, where the goal was to operationalize them. So we did a grant funded by NIFWF in partnership with Archipelago to take some of these fish tracking and counting algorithms, integrate it into Archipelago's review software, and then now we can use the AI results operationally to assist reviewers as they review the data. And so we had some really exciting results from that. We found that they obtained essentially the exact same counts, so a difference of only 1%-ish, but they were able to do it 40 to 50% faster. And so this was pretty remarkable and pretty surprising even for us that such a simple solution could lead to such drastic speed-ups. And so it was a really exciting proving out of the technology. And so we're moving forward with getting this more and more integrated now. And so if you saw Jimmy's talk earlier, he's probably mentioned like our API and different ways that you can interact with this. So feel free to reach out if you'd like to give it a try. Another project we worked on was with EDF, their SmartPass project. I think they're presenting on it here. So we worked on specifically taking some algorithms that they had proved out for counting fishing vessels in small-scale fisheries and moving them to the edge, which means small compute hardware directly attached to the camera at the point that the footage is being recorded. And so what doing this optimization allows us to do is put the algorithms onto these, basically onto the camera, and then you don't have to transmit the footage, you can just transmit the metadata every day of how many boats went in and out of the port. And so that's something that we're deploying right now. And then finally, I'll touch on trawl. This is a project that we're doing with Fisheries and Oceans Canada, DFO. They want to know when a tow comes on board a trawl vessel and there's thousands and thousands of fish on screen, what species are they? It's a really hard problem. You can't do it in the classic computer vision way that a lot of people here have probably seen, where you draw boxes around things. You would have thousands of boxes all overlapping, and it would take up the whole image, and those algorithms just don't work very well. So we've come up with a new way to do it where we can very accurately segment out and count the number of fish on screen and then apportion them into different species groups. And we've built out a little software interface around it, and so this is now being integrated into review software and allowing them to kind of automatically make better apportionment estimates. It's kind of an interesting situation where rather than just trying to speed up the review process, now we can make certain parts of it more accurate. It turns out that when people just look at an image and try to guesstimate what the percentage makeup of different species in the fish pile is, they're not very good at it. And so we kind of compared what's the best case for a human with actually what the algorithm can do, and we found that we can make things a bit more accurate, which is pretty exciting. And that's it for me for today, so thanks so much. Feel free to reach out.